Okay, let me go through up to part 3 and then just give you a bit more time to just finish up D, okay? And then we should move on to the next question because I don't want some of you to be stuck for too long. Alright, okay, let's run through at least up to 3, then D you just complete it. Okay, write the expression for Kc. So this one not a problem. Write an expression for Kc. The unit is moles minus 4 dm12. Okay, this one I expect everybody to be able to do it. Then after that, they say calculate a value for Kc given that O2 has this concentration, whereby the other two are equal. So it's not that difficult. These two values are equal, so they probably cancel out. Alright, and then you just have to sub in the O2. You just sub in the O2 value, and then you can find out the Kc. Okay, so these two will just cancel out, right? Because since they're the same value. So you sub inside, alright, you get this answer. 3 times 10 to the power 20. Of course, the same unit. Right? It's quite a very big value. It must make sense. Why is the value so big? Because this is hemoglobin. It's going to carry oxygen. It must be very big so the equilibrium is very much to the right hand side. Okay, so it must be able to carry oxygen. Right? If it's very small, means you can't breathe really. Right? So it has to be a very, very, very big value. Okay, so that's part 2. Alright. Then use your value of Kc to calculate the O2 needed for 99% of the Hb to be converted. So what it means is this, so imagine I put IC table, right? Use your Kc value to calculate the O2. Okay, this O2, can somebody tell me, I'm not sure whether when we read through this, is this O2 initial or equilibrium? Do you think this O2 they're asking for, is it the initial or equilibrium? Is it initial or equilibrium? Okay, it's kind of strange, but it sounds like initial, but actually it's equilibrium, the O2 at equilibrium. The reason why is because they use your value of Kc, and Kc is all at equilibrium. So to calculate the O2 also at equilibrium. Okay? So they want you to use your Kc at equilibrium to calculate O2 at equilibrium for 99% of it to be converted. So what it means is this, you start with 100%, here you have 0%, so 99% was converted, right? So minus 99%. So this one plus 99%. So what you have left is only 1%, and here is 99%. So essentially, what they want you to do is to have the ratio. So the 99 is to 1. You see, 99 is to 1 is just the ratio. So you will probably have the ratio already. So this is the ratio. 99 is to 1. So you have the ratio. You have the Kc, which you use from here. Then you can find O2. Okay. Okay, and then you plug in the values. So this ratio is 99 is to 1. You see? 99 is to 1. It's just a ratio. Right? So you sub it in. Then you find out O2 and this is the answer. Okay? 2.4 times 10 to the power minus 5. Make sense? Because you just have to sub in this ratio. And I got the ratio by doing that. Alright? Okay, let's try the last part, part D, and then I need you to move on already. I think most of you got a certain part, so that's where you got stuck. Okay, so you're just going to sub in the value. So it's not that difficult. Kc, right? Kc, and then this expression, you sub in the value for O2. Okay, sub in the value for O2, and then you also have Kc. So after getting the ratio, look at the ratio. This is the ratio, 7.6 over 1. Okay, bring it across, 7.6 over 1. So what is this question asking for? Okay, what's the question really asking for? The question is asking for what is the percentage of MbO2. This is oxygenated Mb, the oxygenated compared to the entire Mb, right? Because some are oxygenated, this is the non-oxygenated, this is the oxygenated one. So actually what you want is the MbO2 over the total amount of Mb, whether it's Mb which is oxygenated as well as the Mb that is not oxygenated, and then you multiply by 100%. Okay, so actually this one is 7.6. I wrote it 7.6 over 1 is just to make it a bit clearer to everybody. Okay, so what do you think is this number here? What over what times 100%? So the numerator will be 7.6. The denominator will be 7.6 plus what? Plus 1? Yeah, total. Okay? Then you multiply by 100% and you get 88.4%. Are you me? Alright, it's just the ratio. Okay? Hello? Does it make sense? Yeah. So this is write it this way is a bit more, it's a bit clearer. Because sometimes some of you just saw 7.6. Okay, so this is how it's done, 88.4%. Okay, let's try the next question quickly. I need to move. Okay, you have to do this. What does it mean when they say the gases behave ideally? What are you supposed to use? The gases behave ideally. So you're supposed to use PV equals to nRT. That's a big hint already, right? The gases behave ideally, PV nRT. So our pressure is in Pascal. Okay, it's in Pascal. So take note that this is ATM. So you 1 ATM, if you do not convert, 1 ATM is 101,325 Pascal. Alright? Volume is in meter cube. Okay, volume is in meter cube. So you need to change dm cube to meter cube. So 0.74 dm cube, right? If you change to meter cube, it's 0.74 times 10 to the power minus 3 meter cube. Okay? Change it to meter cube. And then you can find out the n really. Okay? So you must make sure your units are correct. R, of course, is 8.31. Okay, check your answers. Those are the answers at the top. So once you have got that, please move on to the next question. Okay, so we're gonna help some of you. You're supposed to find out you have to find out the number of moles first, right? So now you have to do the IC table. Continue. ICE, but I'm gonna do all in terms of moles. So please find out the number of moles of N2O4. Mass divided by MR. This is the MR of N2O4. Okay, it's 92. Okay, 92. This is the starting number of moles of N2O4. Complete your IC table. Okay, the value here is the total moles at equilibrium, which includes both gases. Alright, at equilibrium. Make sure you got this misconception. Actually, this value is the total moles of both gases. This is the number of moles of NO2 as well as N2O4. Okay, at equilibrium. So this value here is for the total moles of NO2 and N2O4 at equilibrium. Partial pressure is mole fraction times total pressure. I hope some of you all remember. Means after getting the moles is not good enough, you need to do mole fraction times total pressure. I'm not sure. You see the answer. Your x should be what value? Let me see. I think your x should be 0.0102. Okay. So the partial pressure, just check. Okay, I think I just put them. Your answer should be 0.34 something at least. I mean 344 or whatever, but it's 0.34 something. So it's the mole fraction, right? The mole fraction, right? So the number of moles here is actually 0.0204, right? The number of moles here is actually 0.0398. Check. Okay, just to do a quick check. Roughly should be about there. Mole fraction times total pressure, mole fraction times total pressure, you should get this value. Check why some of you the numbers are a bit off. Okay, so check again. See why some of the numbers are a bit off. Alright, okay, let's move on. Over here, the first one, 2. 2 is actually equals to Hi square. Okay, the value 2 is equals to Hi square over H2 times I2. Okay? Okay, what they want is actually H2 to the power half, I2 to the power half over Hi. Okay, so very quickly, you can see that's a bit inverted, right? So if I flip this, if I flip it as H2 times I2 over Hi squared. Okay, if I do that, this value will be half, correct? Okay, but I don't want this, I want this. So how to convert from 1 to 2? How to convert? I do what? Square root. Because everything is to the power of half. Can you see that? Everything is to the power of half. If I do that, then I get this. So actually the answer is 1 over square root 2. Okay? Are you me? Okay, so that is square root because it's to the power half, right? So you have to the power half, everything is to the power half, right? Okay, let's try this one. This is actually not too difficult. I think most of you got it. Right, answer is C. So I think those who didn't get it, maybe I just run through for the few who didn't manage to get it. Okay, so I'm going to write down very quickly ICE. Right, ICE, yeah? So I started with X and 3X. Alright, X and 3X. And then they say 50% of nitrogen and reactants minus 0.5x. So the ratio is 1 to 3. So if minus 0.5x reacted, here be minus 1.5x. Here is 1 to 3. This one is plus x. Okay, the ratio is 1 is 3 is to 2. So you can see the change always follows the stoichiometry ratio. So this is 0.5x, this is 1.5x, and this is x. Right? Add them together is the final pressure. The final pressure was P, add them up. okay, 0.5x plus 1.5x plus x, right? So that gives you 3x. Okay, all add up is 3x, right? So 3x equals to p. So easy. So x equals to p over 3. Okay, so this is actually not so difficult. The answer is C here, okay? Okay, so that's how it's done. Just do a quick proof already. Yeah? Okay, let's try this one. This one might be a bit more tricky. This is the A-level question. This one a little bit more tricky. So I'm going to work it out nicely and hopefully everybody can get it. Okay, if you read through carefully, they say this. The value of the pressure P is found to be 20% greater than if only P were present. If only P were present. If only NO2 was present. So the pressure P is only when NO2 is present. So I'm going to write IC table here. Okay, just do this one more time. Okay, so this is here P. Okay, if only NO2 was present, it's P. Okay, ICE. So actually, you see, notice that there are 2 moles of gas on this side, 2 moles of gas. And then after some time, there will be how many moles of gas? 3 moles of gas, right? So which means the pressure must increase. Okay, and they say increase by 20%. Right, increase by 20%. So this is how we do it. P00 minus 2x plus 2x plus x. Alright, so become P minus 2x, 2x plus x. Okay, add up everything. Add up everything here. Okay, if you add up everything, you realize this is actually your P plus x, right? And this is how many P, I know? It's 20% greater. The final pressure is found to be 20% greater than the original. So this is how many P? 1.2 P. Good. If this is 1.2 P, you know what's x? X is 0.2 P. Okay? So that's good. Okay, so finally, what's the mole fraction of oxygen? So I want a mole fraction of oxygen. So mole fraction, this is mole fraction, right? It's actually number of moles of, take it as number of moles of oxygen over the total moles, right? So the number of moles of oxygen, we take it to be, we just take it simply to be x, okay? The total is how much? Total is everything. It's actually P plus x. Everything, okay? Right, everything at P plus x. Okay, but not done yet. So I'm going to just simplify because we can actually simplify it. X, we realize that x is how many P? X is actually 0. It's proven already. X is actually equals to 0.2 P, right? So I'm going to put 0.2 P. And P plus x is actually how many P? 1.2 P. It's okay? So this is a proof. So the moles, like take the moles over the total. Right? The moles over like the total, right? So x is the like as if the moles of NO2 O2, and then this is the total. So you plug it in. That's why the answer is going to be 1.6. Okay? Alright, that's why that's the answer A. Okay, so it's a bit of manipulation, but you must understand what they're doing. Okay, you must understand about the 20% greater. Alright? Okay, let's move on to LCP. So I'm going to teach you some of the concepts and then you start doing some questions. Okay, very, very simple. Alright, LCP, the concept, there are a few conditions that you must change, right? It's pretty straightforward. Okay? Alright, so this is the proof of how it was done really. Done, Okay, so let's run through this next part. Okay, please memorize the LCP principle. If a system at dynamic equilibrium is subjected to a change, okay, the first thing, the system is already at equilibrium. And then you subject it to a change. The change can come in 4 forms. You can change the concentration of the reactant or product. You can change the pressure of the system. You can change the temperature, or you can even add a catalyst. So the change will disturb the equilibrium. The system will respond in such a way as to counteract. So counteract, okay? So it will just counteract the effect. Okay, after you counteract the effect, a new equilibrium will be established. Alright? So let's see how it works. Okay, it's pretty straightforward. We're going to do one by one. So start with concentration. Okay, let's start with concentration. Okay, so this is the idea. You have A plus B to give you C. Okay, A plus B will give you C. So can you see this line, straight line, right? So which means everything here was already at equilibrium. Okay, starting, everything was at equilibrium. So you're going to add in A. Okay, I'm going to add in A. So this one bump up. Okay, look at the graph. I want everybody to learn how to interpret the graph. So this one went up. Okay, go up because A was added. Alright, added A. So this one went up. So when you increase A, equilibrium will shape where? If you increase A, equilibrium shift to the system will try to decrease the A. So in order to decrease the A, it must shift to the right, okay? So addition of A, the system will try to remove, highlight, you must always explain why, the system will try to remove the A, right? How to remove the A? Means A must become lesser and lesser, so position of equilibrium shift to the right. Okay, shift to the right. So there'll be lesser and lesser A, and then more and more C. So more A and B will react to produce C, and then take note, Kc remain unchanged. Kc is only affected by temperature. So if I don't change temperature, the Kc will still be always the same value. Okay, Kc is only affected by temperature. I don't change temperature, Kc still remains the same. So let's see how it works. So C will start to increase, as you can see, C will start to increase until reach the new equilibrium. A and B must drop, so B will start to drop, alright, and A will also start to drop, okay? Yeah, A will start to drop. Okay, one thing I want to take note of is this very, very important concept as well. Whenever you bump up the A, and then it starts to shift right, the new equilibrium, the new equilibrium value is somewhere in between the original and the amount that you put in. It's always within this gap. You see? So you start with A, boom, went up, and then it starts coming down. It always comes down somewhere in between. If you sketch something like going down like that, you get 0 already. Okay, you always fall somewhere in between. Okay, so take note, it's always going to fall somewhere in between. Alright, okay, I think I can have, let's see, okay, I just want to show you a little video, I think we can do that, and then we try to fill in the gaps, fill in the numbers here. Okay, so let's think through, okay, you see whether you can understand this, Okay, this is just to show you a bit like what's equilibrium, okay, what's equilibrium. So, okay, let's see how it works. So I'm going to say I'm going to add in more nitrogen. Okay, something that is equilibrium already, right? So if I add in increased concentration of nitrogen, this is what I get. Okay, I put in more nitrogen. Alright, so this is what becomes a bit heavier, a bit unbalanced really. So how will equilibrium position shift? Because it means that this one is a bit heavy already, right? You produce more, you must get less and less of this. So it will shift where? Shift to the right. Good. So the equilibrium will actually move. So nitrogen and hydrogen will start to react, and then you shift to the right, and then until it reaches a new equilibrium again. Okay, see that? Okay, now I'm going to do this. I'm going to remove ammonia. I take away ammonia. Take away. Equilibrium shift where? I take away ammonia, right? That's why it becomes this way, right? So how will equilibrium shift? Right or left? I take away ammonia. The system must try to produce more ammonia, isn't it? So we'll still shift where? Shift to the right. Yeah, it's good. It still will shift to the right. So if you decrease this, by LCP, it wants to increase this. So equilibrium must still shift to the right, produce more of this, okay? And then after that, reach the back the same equilibrium. That's all. Okay, so it's a very, very simple concept. Okay, so let's fill in the blanks now. It's a very, very simple concept. Okay, let's fill in the blanks. You should be able to get it. Okay, so then after you can start doing a question, alright? Okay, so do this with me very quickly. So equilibrium shift right or left? Just tell me right or left. Increase concentration of reactant. You'll shift right because it wants to decrease the concentration of reactant, right? So the reactant must increase. Okay, I take away the reactant. Means it's A plus B, or A, just give a simple one. I remove A, take away A. So equilibrium must shift to the left to produce more A. Shift to the left. What happens if I put in more product? Sorry. What if I put in more product? A and B, right? So very quickly, if I increase B, shift where? Left, because it must make B lesser and lesser. So it must go here. Well, quite easy, yeah? So of course, if I take away B, like just now, take away B, must produce more B, it will shift right. Okay, very straightforward. Okay, let's try the question. It's pretty okay. What will the OH minus react with? Tell me very quickly. What will the OH minus react with? Yes, H plus. So what happens to H plus concentration? Decrease. Okay, so that's the first statement you have to write. With the addition of the alkali, it will react with the H plus, right? Then the H plus concentration drops. So the first thing I expect you to write is concentration of H plus decreases. Okay, you must be able to see that the OH minus reacted at H plus. Concentration drops, right? So you must say when H plus concentration drops by LCP. I think some schools are very strict. They don't allow you to write LCP. They want you to spell out everything. So by Le Chatter's principle, you say the position shifts to the left. Okay, but you can't just say shift to left. You must always explain why it wants to shift to left. So the Y part is important as a marking point. So I want to see you write not just shift to the left. The Y part is to produce more H plus ions. Okay, right there? So if you don't have this, you'll be losing some marks, right? To produce more H plus ions is a marking point. Just shift to the left, that's it. Okay, you must say Y. The Y part is always important when you do LCP, Y, to produce more H plus ions. As you produce more H plus ions, you know that you get more of this. So the solution will turn yellow, Kp remains unchanged. Okay? Actually, this statement you don't write is fine. And then I just read in my notes so that I focus the fact that if you don't change temperature, Kc always remains the same. Okay, so actually if you look at this question, right? When you added the base, it affected this part here. Can you see? It affected the H plus concentration. If Kc didn't change, right, it means that equilibrium must shift really. Is that? Yeah, Kc didn't change. Okay, let's try this one here. So this one here, what happens when you add in silver? Equilibrium shift where? Shift where? Actually, this is a solid. So what if it's a solid? So if it says a solid, right, you know how I write this expression? Fe3 plus, also put silver? Ag plus, you all wasted your pen ink already. Over here is Fe2 plus, right? So when I added silver, the silver adding solid is not here, right? Did it affect any of these? Nothing was affected. So actually no shift. Okay? Because nothing was affected. Yeah, no shift. It's a solid. Solid not even inside here, right? So this is how you have to write it. Ag silver solid is not even in my Kc, not inside here. So since concentration of a solid is always a constant and doesn't change, right? So adding Ag plus will not affect the position of equilibrium. Hello, me? Because the silver not even inside here. So you add in also nothing changes. Okay, unlike the first one, the Kc still affect H plus, right? This one didn't affect anything. Hydrogen bromide is allowed to dissociate at equilibrium. Okay, at equilibrium is this part, initial equilibrium. Initially it was already at equilibrium, 0.8, 0.1, 0.1. Initially already equilibrium. So how much HBr did you add in? You added 1 mole of HBr. Okay, they said you added 1 mole of HBr. Okay, so when I add 1 mole of HBr, we know that equilibrium will shift to the right, it starts to shift. So this is the representation of the change because it's trying to shift already. So when it shifts to right, you must what do you write here? Minus what? Yeah, I don't like to see fraction, so I'm going to put minus 2x. Then the side plus x, and then here also plus x. Why? It's shifting to the right. Okay, so this is what I'm going to write down. Okay, continue please. I'm helping you up to here. Okay, the change minus 2x plus x, that change is because it's shifting already. Okay, I'm going to save you some time. Okay, so I don't need you to solve it. Okay, I don't need to solve it. Yeah. Okay, I don't need you to solve it, but I'll just show you. So I think up to here is fine. Check. Okay, 1.8 minus 2x, 0.1 plus x, 0.1. It's okay? Can? Then I divide by the volume. Okay, divide by volume, which is 2. So far, good? Yeah. Then you sub it inside. Actually, it's not that difficult to solve. You think about it, right? This times this over this square, right? So it looks like that. In fact, they are the same. So that's why on top here is a square. So what you can do is you can do square root on both sides. Okay, you can do square root both sides. If you do square root both sides, this is your final part. 0.1 plus x over 1.8 minus 2x equals to plus minus. You square root that, it's actually a nice number, 0.125. And I need to solve it now. Okay? So we'll save some time. I don't think I need you to solve it here, alright, because it's quadratic, actually not really quadratic. Once I do it this way, it's not quadratic anymore. Okay, so you solve for x will be 0.1. Yeah, okay. So the amount of bromine at the end is this one here. Yeah, 0.2. Okay, but I won't make you solve it here. I take it as you can do it. Okay? It's maths only, right? Okay, over here, this is how it works, right? You started with Q. So this is the concentration of Q. Alright, just make sure this is 10, okay? Equilibrium for Q is 10, so 10 is like that. Equilibrium, 10. Then what will be the new equilibrium if 5 moles of Q is dissolved? Let's just throw in another 5 moles of Q, so you'll bump up. Okay, bump up to 15, okay? Bump up to 50. And then once you increase amount of Q, right, you know that equilibrium will shift where? To the right, okay? And then you start to drop. And I told you just now it will drop somewhere what? In between, okay? In between, can drop somewhere in between. So the answer will be A. Okay, the answer will be A. Alright? Okay, so let's do this one. So this is somewhere in between, the drop. Okay, and this is somewhere in between. Okay, so it's A, Get it? Okay, let's try the next one. Okay, this one is not so difficult. I think this one you probably know what to do. So you started with this. It was actually present at equilibrium. This two straight line. You can just draw a bump up to A. So A increase. So equilibrium will start to shift to the right. Okay, so B will start to increase and A will start to drop. So I guess you must draw A starting to drop, and you reach equilibrium, B starting to increase until it reaches equilibrium. See, but what I want is you to tell me is not very nice, but what I want you to know is the final value here. Okay, what's this value here, and what is this value here? Okay, what's this value? So let's see how we do it. So in order to find out the value, we have to do like the IC table. Okay, so A, okay, do me. I'm going to show you. A to B, right? So I started with how many A? I add, change, equilibrium. Okay, let's fill in the numbers. A was at first 2, B was at first 1. So after that, what? You add in what? What do you add in? Add in A, right? So you add in 1 plus 1. Okay, plus 1. So when you added A, equilibrium shifted to the right, so minus X. Okay, so first good, plus X. Okay, so finally, what is this part? 2 plus 1, this one like just what we did, right? It's 3 minus X. That side is 1 plus X. So this is the equilibrium, isn't it? So we know Kc is equals to 1 plus X over 3 minus X. So far so good? Okay, but what's Kc? In order to get X, I need to have Kc, right? Is Kc given? Is Kc given? Kc is given. What is Kc? You all missed out that actually this whole system was already at equilibrium. Means you know the Kc. So what's Kc? Kc equals to what? B over A, right? So it's actually and you have to pick up your Kc from there. We don't have to give it to you. Okay? And I told you Kc didn't change, right? I didn't change temperature. Okay? I didn't change temperature. Kc is the same. So work it out. Kc is actually half. And then you work it out and then find out X and you're done already. Okay, I'll teach you next concept. Okay, so the learning point is must look up for Kc. Right? As long as equilibrium, you can get Kc. Is okay? So I trust everybody have calculated done, right? It shouldn't take too long. So the math, I think once you got X, it will be 1/3, and then you just sub it in. So B should be 1 and 1/3, A be 2 and 2/3. Okay? You get it? Hello? Can? Okay, so this is done. So the learning point is to make sure you can find out Kc from there. Can? Okay, let's move on. Okay, I'm going to teach you this concept. This is dilution. So this is a bit tricky, so pay attention and see what happens. Okay, they say predict, explain what will be observed when water is added to this system. Okay, what's this system? This system has pink and blue color, pink and blue. So you're going to add water. So if I look at my Kc, right, Kc is this. So I guess it's all aqueous liquid. So water is a solvent, it is in excess. So I will actually don't have to put water here, right? So it's going to be like COCl 2 minus over CO H2O 2 plus, and then Cl minus to the power 4. Okay, good. So can you tell me what will happen when you add water? What will happen when you add water? Equilibrium shift right, shift left, or don't shift at all? Will it shift right? Will it shift left, or no? Okay, the thing is this, because our focus is on water, right? So this water here is not even inside here, right? Okay, but the truth is this, it will actually still shift. Okay, why will it still shift when you add water? Because when you add water, you know something? Yeah. When you add water, what happens to the concentration of this? Don't look at water here, but what happens to the concentration of all of them? It will decrease. And see, the concentration for everything will decrease, right? Even though water isn't in the expression here, but all these are aqueous solution will drop. So let's try and think through what will happen. So this is how you think, but this is for dilution concept. Usually it's quite tricky. So you add water is actually dilution. So the concentration, I'm going to use this word, concentration of ions. ions, because the ions are all the soluble ones. See, all the ions are soluble. So concentration ions decreases. Okay, by Le Chaste's principle. What does it want to do? We want to do the opposite. We want to increase the concentration of ions. So what does it mean? If you want to increase the concentration ions, it has to shift right or shift left? Shift right, shift left? Or does it shift? Yeah, because how many ions over here? 1 plus 4, right? We take it as over here there are 5 ions. Okay, 1 plus 4. So this one only have, this whole thing only have 1 ion. Which means it must shift to the left. Shift to the side with more ions, okay? Because I want to increase concentration ions. Okay, so they're going to shift left. Shift aside more ions. So maybe you can copy this down. So addition of water reduces the concentration of all the aqueous ions. So to re-establish equilibrium, it will shift to the left. It will shift to the left to increase the concentration of the ions. And the solution will turn more pink. So this is a dilution concept. It's a bit tricky. It always shifts to the side with more ions after dilution. Okay, I'm going to show you mathematically why is it like this. Mathematically. Anyway, you copy this first. It's okay? So we shift to the side with more ions. Okay, there's 5 ions on the left, 1 ion on the right. Okay, let's try. I just give you a simple idea. So say for a hypothetical question, right? All the concentration at equilibrium is 1. So actually everything is 1. Okay, imagine I double the volume, add water until the volume doubles. So when the volume doubles, right, there's a new QC, right? QC is at any point in time. So actually when I double the volume, what happens from this is 1, this is 1 at first, all 1. So if I double the volume, you notice something, all the concentration will half, right? So actually this becomes half. This one becomes half, and this one becomes what? Half, right? To the power of 4. Cancel. Actually this is 16. Make sense? So but 16 is not equilibrium. It must go back to what? It must go back to what value? It must shift until go back to what? 1, right? So how to go back to 1? Means the value must start to what? Drop. Okay, the value must start to drop. So if the value must start to drop, it must start to drop. What does it mean? It means that this value must what? Tell me, increase or decrease? 16 must drop to 1, you know. So this value must start to decrease. And this one must start to increase. And really what's happening is shifting where? Shifting to the left. Can you see that? So you have more of these two and this one will drop. Yeah? Okay? So this one is a dilution concept. Okay, let's look at the next one, gases. Okay, now it's talking about pressure. Alright? Okay, pressure is pretty straightforward. Okay, pressure. So there are only two types of questions whereby one side has more gas molecules compared to the other. Right? So this one has 1 mole of gas and this one has 2 moles of gas. Right? We are looking at gases. Now we are learning about pressure. So if the total pressure is increased, by Le Chaste's principle, it wants to decrease the pressure. So highlight. It wants to, when you increase total pressure, it wants to decrease the pressure. Okay, it wants to decrease the pressure. So in order to decrease the pressure, it must shift to the side with what? More gas or fewer gas? It wants to decrease the pressure, it must shift to the side with more gas molecules or fewer? Fewer. Good. I want you to highlight this. It must always shift to the side. Shift to the side with fewer gas molecules. Highlight. And an important marking point is you must put the word gas molecules. Fewer gas molecules. Okay, you shift to the side with fewer gas molecules. So you shift to the left. Okay, very simple. Just shift to the left. Okay, so you shift to the left to the side with fewer gas molecules. Okay, what about this one here? If they're the same number of moles of gas, this one 2 moles of gas, this also 2 moles of gas. So if I increase the pressure, where would it shift? If the number of moles of gas on both sides are the same, they won't shift. Yeah. Okay. So do mention, if they say what happens if total pressure increase, please mention that since the number of moles of gas on each side are equal, there will be no shift in equilibrium. Okay. So you're gonna please mention number of moles of gas on each side are equal. So there's no shift in equilibrium. Okay. Let's try the question. Okay, the degree of dissociation later when you do it, understand it's actually the change over the initial times 100%. Okay, work it out, okay? So this one actually you need to do the IC table. Okay, so if you did the IC table, it's like that. 0.30 minus x plus 2x. So in fact, everything here, so don't get mistaken. All these are rate 8 here, right? So these are already the partial pressure. These are not moles. These are already partial pressure. So you add them all up, these two, you're gonna get 0.5. Okay, you add them up. This plus this, right? Add it together, you get 0.5. Then you solve it. Okay, X is gonna be 0.17. So they say calculate the partial pressure NO2. So NO2 is partial pressure of NO2 is actually 2x. That's all. So this is really partial pressure. So X is 0.17. So 2 times 0.17, this is 0.34, okay? So this is really the partial pressure straight away, okay, ATM. Okay, then if you find the KP, work it out, you get 0.723, alright? So this is this is 0.34. You sub in the X here, this should be 0.16. Then you get this. Simple? Right, so the degree of dissociation, not difficult. Okay, the degree of dissociation, not difficult. All you need to do is the change over the initial, then you times 100%. So the change is 0.17 divided by initial times 100%, okay? So not too difficult. Okay, let's do the last part. Okay, up to here, I think most of you got it. So initially, let me see here. This actually, maybe just to let you know, this gas is actually brown. Okay, maybe you can write down. You must know NO2 is brown, and this guy here is actually colorless. Okay, actually it's colorless. Okay, N2O4 is colorless, but NO2 is brown. So at first you have this NO2 brown and N2O4 which is colorless. So generally this is what you have originally. Okay, maybe I just show you a picture here. So this is because it's NO2 is brown color. Alright. So now you're gonna double the volume. So it's gonna look like that. You're gonna double the volume. So if you double the volume, it's gonna look something like this. Okay, this is what it looks like. Okay, so I'm just going to show you roughly what it looks like first. So when double the volume, actually the color becomes lighter, right? Okay, because the volume expands, right? Bigger volume. So but the important thing to take note is when you double the volume, what happens to the total pressure? When you double the volume, the total pressure will decrease. Yeah, decrease. So when total pressure decrease, what happens? Okay, equilibrium will shift where? It wants to what? Increase the pressure, right? Will increase the pressure. So you shift to the side with more gas molecules, right? Here got 2 moles of gas, you only have 1. So you shift to the right. So over time, you get more NO2, and then when it reaches equilibrium, I think the color looks as brown again. Okay, because you're shifting to the right, produce more NO2. It's okay? So it's about the total pressure decreasing when you actually double the volume. Okay, if you know that, then it's pretty straightforward. Okay, I'll let you copy the answer. I think I have it over here. Okay, so just write this down. Okay, when the volume of the gas mixture is increased, okay, when the volume of the gas mixture is increased, the important thing is you at least must take note the total pressure is decreased. Push it higher. Okay, anybody need to copy the top part later? I just let you see for a while. Okay, by LCP, the system will try to increase. We'll try to increase the pressure by forming more gas particles, gas molecules or gas particles. The word gas must be there. This is the marking point, more gas particles. So shift to the right. Okay, so actually I forgot to answer the question. So if you shift to right, it increases the degree of dissociation. Right? It means more dissociate. So I mean the thought process is this, when the volume increase, right, volume increase, the total pressure decrease. Okay, that's the first point. When total pressure decrease, the system by LCP, it wants to increase the pressure. Okay, so next point, talk about it must shift to side. I'm just giving a quick summary, side with more gas molecules. Okay, then you ask yourself, hey, shift to which side? Which side is more gas molecules? In this case, right hand side, so shift right. Okay, so not that difficult. Alright, so if shift right, degree of dissociation will increase. Okay, let's look at the last concept we're going to teach for today. I'll talk about temperature. Okay, temperature. Okay, temperature, you just have to understand one important point, two important points. You probably can do quite a lot of questions already. Alright, so I'm going to try to summarize for everybody. Okay, so I think it's okay for this? Yep. Alright, okay, let's try. This gas is actually quite, normally it's quite okay for pressure. Right? Okay, Okay, let's try this one now. So temperature, last part up. So temperature will change two things. Temperature, when you change temperature, it will affect two things. It will affect the position of equilibrium. It will also change the Kc value. Alright, so now this is an additional thing. It will change the Kc value. Alright, so let's try. So if a reaction is endothermic, like this one, plus. Okay, this is endothermic, endo. Okay, let me go through, then after that I tell you what you should learn by heart. Okay, and then hopefully that will help you to do more questions. So when temperature is raised, maybe you can take note of, when I increase temperature, so what I'm doing is I'm adding heat. Add heat. Okay, you're adding heat. So by LCP, of course, it wants to do the opposite. It wants to what? The opposite of adding heat is remove the heat. Absorb heat or remove heat is fine. Okay, the word I want to use is the system will try to remove or absorb the extra heat. Take away the heat. Okay, adding heat, the system will try to take away the heat. Alright, the word is remove or absorb. So because you're absorbing heat is favoring endo-exo. Absorbing heat is endo-exo. Endo. So you must say endothermic reaction is favored. Okay? So you want to absorb heat must favor endo. So then I will look at the equation and ask myself, where's endo? Endo is forward or backward reaction? Forward. So you must write down, since forward reaction is endo. Okay, look at it and say, where is the endo? So forward is endo, please write forward reaction is endo. So equilibrium position. So equilibrium position, sometimes short form is position or equilibrium, right? That's how we write down short form. Position equilibrium will shift to the right, favor endo. Okay? And then, next part. So if you shift to the right, what happens to Kc? Because Kc is actually C times D over A times B, right? So this is the time that Kc will change, temperature. So you shift to right, C and D here will increase. B and A will decrease. So Kc will increase. So this is the point where I change temperature, Kc will increase. Okay, let's try one more where temperature is lowered. And then after that, please, we can actually do questions already. Okay, help me out. When temperature is lowered, okay, lowered means we actually took away some heat. Okay, so heat is actually being removed. Okay, heat is actually being removed. So by LCP, what does it want to do? What's the word you're going to use? The system must try to what? Release heat or produce heat. You can say release heat or produce heat. You can take away some heat, you lower the temperature, it wants to raise the temperature. So you try to produce more heat or release heat. So to produce heat, it must be what? Endo, exo? Exo. So right, exo is favored. Okay, exo is favored. So to produce heat, it must favor exo. Okay, this is how I'm going to write it. I won't even bother to say, I will ask myself, if they say exo is favored, I look at the equation and say, exo is forward, backward. Exothermic reaction here is forward, backward. So instead of saying, since forward reaction is endo, hence backward reaction is exo, just look at it and say, backward is exo, straight away. Backward reaction is exo, okay? So you save some writing. Since backward reaction is exo, so it will go left, backward, favor left. Okay, go backwards. So backward reaction exo, it favors exo, it will shift left. Then Kc will decrease. Okay, Kc will drop. Okay, so let's see what I want you to learn. Right, you copy this down, and then later on you can do all the questions today. Okay, change in temperature. Okay, this is only for change in temperature, right? Kc increases. What does it imply? I change temperature, Kc increases. What does it say about position of equilibrium? You say I change temperature and then the Kc value went up. Means I know that the position of equilibrium shift where? Shift where? Right, good. So if Kc drop, means position of equilibrium shift where? Left. Okay. But this only happens for what? Change in what? Temperature, because Kc only change when temperature changes, okay? So take note. Alright, okay, next one. So this is important, learn it by heart. Okay, another one I want you to learn is this. Increased temperature will favor endo-exo. I add in heat to the system. The system will try to what? Absorb the heat, right? So you try to absorb the heat means must favor the endo. Good. So learn by heart also. When I drop the temperature, the system wants to increase the temperature. So in order to increase the temperature, it must favor exo. Okay, if you can remember these 2 points, you probably can do most of the questions. Okay, so these are the important concepts. Alright, how Kc will tell you how the equilibrium shift. Temperature will tell you will favor which kind of reaction. Okay, let's turn over to the next slide. We just do a quick summary, and then I want you to do the questions with it, right? So let's do a quick summary at the bottom here. Okay, that'll be good enough. Okay, so let's run through. Okay, this is let's run through this part. Fill in everything. If you can do this part, you get it. Okay, the first part is this: A plus B. Oh no, just A to B. Okay, keep it simple. A to B is exo. A to B, change in H is minus exo. Okay, the next one, A to B is endo. Okay, positive. Okay, and endo positive. Okay, let's try. So when I increase temperature always favor. Increase temperature, you add in heat system, the system try to absorb. So always favor. Increase temperature, add heat, the system try to absorb, right? So favor the endo. Shift right or left. Forward is exo, backward is endo. So shift left. So when shift left, Kc will increase or decrease? Go backwards. Hello? If you go backwards, if you're going this way, drop, increase. So Kc will decrease. Good. So it's quite okay. Okay, let's try the next one. When I lower the temperature, the system wants to increase temperature, will favor exo. Good. Okay, maybe I write down here. Sorry, I did some space here. I write down here exo first. So exo, then you look, forward is exo, right? So shift where? Right. So whenever shift right, this Kc will increase. Okay. Okay, one more and then you do the rest. Okay, last one. This one, because now the reaction is endo. Okay, let's try. Increase temperature, favor. Increase temperature always favor endo. Shift right. Right, endo right. Shift right. Shift right, Kc will up. Okay, and then done already. Okay, let's try 2 slides and then we'll stop. Okay, make sure you can understand and write according to how you're supposed to write. So normally this is the format of how I want students to write. Okay, this is a format. Okay, so let's see whether you can do it. Okay, just do 2 slides, then the rest will be homework. It's all about temperature. Okay, so let's run through the first slide and then do the second one. I think most of you are okay already. So increase temperature, at high temperature, adding heat, the system will try to absorb the heat. I want to see the word absorb the heat, okay? Make sure you have that in your answer. Okay, the system will try to absorb the heat. It will favor endo. Okay, it will favor endo. So there's a since forward reactions endo. Since forward reactions endo. So forward reactions endo, right? Since forward reactions endo, position equilibrium shift to the right. Done. Okay, very easy. So you shift to right, there are more product than reactants. Kc will increase. Okay, do mention about Kc. Alright, whenever we talk about temperature, right? Kc will increase. Okay, pretty straightforward. Okay, this one here. This is the tricky one. There's actually 0. So this reaction is not endo, not exo. So which means there is no reason why it should shift at all. Okay, it won't favor any side because it's neither endo or exo. So since change in H is 0, maybe I should write this down. Since change in H is 0, okay, the top part, this one is okay, right? This one, change in H is 0. Reaction is neither exo nor endo. Okay, the reaction is not exo, not endo. So position of equilibrium will not shift left or right. Okay, so with increase in temperature, hence Kc remain unchanged. So it's only this condition that Kc doesn't change when temperature changes. This is the only condition when change in H is 0. This is the only condition where I change temperature and yet Kc doesn't change. Alright, so this is like the exception. Okay, the exception. Okay, let's try the next slide. This is okay, I think most of you at least can tell me Kc doesn't remains unchanged and then doesn't shift. Okay, let's run through. I think not too difficult, just look at the marking points. So first part, this one maybe it's good if you can tell me even what bond is broken because I already give it to you. To form NO2, this bond must be broken. Okay, so this is breaking the NN bond. NN bond must be broken, hence for reactions endothermic. Okay, let's look at next part. How equilibrium will change when temperature is decreased. So when you lower temperature, means you want to increase temperature, it will favor the exothermic reaction. Okay, so this one really we know is endo. Alright, it's endo, but it will favor exo. So it must shift backwards. Yeah. So let's run through. When temperature is lowered, okay, when temperature is lowered, by LCP, the system will try to produce heat, either produce heat or release heat. Favor exothermic, okay, favor exothermic. Then just mention, since backward reaction is exothermic, right? Just run straight to it. Since backward reaction is exothermic, it will shift to the left, okay, and Kc drops. And they ask for observation, please write down the brown color starts to fade. They ask for observation. Okay, as you shift left, the brown color starts to fade. From brown to colorless. Okay? Right, because the NO2 was brown. Okay, this one also quite okay. I think most of you got it. It was repeated at a higher temperature. So this one is the opposite, right? When higher temperature, increased temperature, the system will try to absorb. So favor endo. Favor endo means position of equilibrium shift right. Shifts right. So if it does shift right, you produce more NO2, right? So 2 marking points. Okay, so I think some of you drew like that. This will be marked wrong. 2 marking points. Firstly, the NO2 at higher temperature will be more. Secondly, I want to see a steeper gradient here because a steeper gradient represents a what? A faster rate of reaction. So don't draw along this line. Please draw a line that sticks out a bit more. Okay, show me that it's a faster rate of reaction because temperature is higher. Okay, so that's the 2 marking point. Rate as well as higher.